Greetings, explorers. Today we embark on a journey to unravel a mystery that has captivated scientists for centuries. We're diving deep into the heart of our planet to understand the powerful forces that shape the very ground we walk on. Join me as we explore the fascinating world of tectonic plates. The Earth's surface may appear solid and unchanging. However, beneath our feet, a different story unfolds. It's a story of constant motion, a slow, relentless dance of massive plates that make up our planet's outer shell. Our journey begins in the early 20th century, a time of great scientific discovery and exploration. Among the many brilliant minds of this era was a visionary scientist named Alfred Wegener. Wegener was not just a meteorologist, but also a geophysicist and an explorer whose curiosity knew no bounds. He observed something peculiar about the shapes of our continents. When he looked at the world map, he noticed that the coastlines of continents like South America and Africa seemed to match up almost perfectly. They seemed to fit together like pieces of a giant jigsaw puzzle, suggesting that they were once joined together in the distant past. This observation led him to propose a revolutionary idea: continental drift. Wegener suggested that the continents were not fixed in place, but had slowly moved across the Earth's surface over geological time. Wegener theorized that the continents were once united in a single supercontinent he called Pangaea. This supercontinent began to break apart around 200 million years ago. Over millions of years, they slowly drifted apart to their present positions, carried by the movement of tectonic plates beneath the Earth's crust. His idea was met with skepticism. Many scientists of the time found it hard to believe that such massive land masses could move. Wegener lacked the mechanism to explain how such massive land masses could move. It wasn't until the mid-20th century, with the discovery of plate tectonics, that his theory gained widespread acceptance. For decades, Wegener's theory remained controversial. Then, in the mid-20th century, new technology allowed us to explore the ocean floor in unprecedented detail. What we found there was astounding. Vast mountain ranges, known as mid-ocean ridges, snake around the globe like seams on a baseball. At these ridges, molten rock from the Earth's interior rises to the surface, creating new oceanic crust. This process, called seafloor spreading, provided the missing piece of the puzzle. It explained how continents could drift apart as new crust pushed them along. The theory of plate tectonics, born from the discoveries of seafloor spreading, is now supported by a wealth of evidence. This groundbreaking theory has revolutionized our understanding of Earth's dynamic nature, explaining not only the movement of continents, but also the occurrence of earthquakes, volcanic activity, and the formation of mountain ranges. Fossils of identical species found on continents now separated by vast oceans tell a tale of a once-connected landmass. These fossils, such as those of the ancient reptile Mesosaurus, provide compelling evidence that the continents were once joined together in a supercontinent known as Pangaea. The distribution of these fossils across different continents supports the idea that the landmasses have drifted apart over millions of years. Magnetic stripes in the ocean floor, mirroring each other on either side of mid-ocean ridges, provide a record of Earth's magnetic field reversals. These stripes are like a barcode, recording the history of Earth's magnetic field as new crust is formed at the ridges and spreads outward. The symmetrical pattern of these magnetic anomalies on either side of the ridges is a key piece of evidence for seafloor spreading. These reversals are imprinted in the newly formed crust as it cools. As molten rock rises from the mantle at mid-ocean ridges and solidifies, it locks in the direction of the Earth's magnetic field at that time. This process creates a permanent record of magnetic reversals, which scientists can study to understand the history of plate movements. The patterns confirm that new crust is continuously generated at the ridges and spreads outward. This continuous creation and outward movement of oceanic crust is a fundamental aspect of plate tectonics, driving the movement of the plates and reshaping the surface of our planet over geological timescales. Seismic data, measuring the vibrations within the Earth, reveal the boundaries where tectonic plates interact. These interactions can be convergent, where plates collide, divergent, where plates move apart, or transform, where plates slide past each other. Each type of boundary is associated with specific geological features and activities. Earthquakes and volcanic activity occur predominantly along these boundaries, marking the ongoing dance of the plates. The movement of tectonic plates is a slow but powerful force, shaping the Earth's surface and driving the geological processes that create mountains, ocean basins, and other features of our planet's landscape. Understanding these processes helps us to better predict natural disasters and appreciate the dynamic nature of our world. Section 5. The engine within mantle convection. But what drives this relentless movement of the tectonic plates? The answer lies deep within the Earth's mantle, the layer beneath the crust. The mantle, though solid rock, behaves like a very viscous fluid over geological timescales. Heat from the Earth's core creates convection currents within the mantle. Hotter, less dense material rises, while cooler, denser material sinks. This continuous circulation exerts drag on the tectonic plates above, causing them to move. The interactions between tectonic plates create some of the most dramatic features on Earth's surface. These massive slabs of the Earth's lithosphere are constantly in motion, driven by forces deep within the planet. Their movements shape the landscape, giving rise to towering mountains, deep ocean trenches, and fiery volcanoes. When two plates collide, they can buckle and fold, pushing up immense mountain ranges like the Himalayas. This collision is a slow but powerful process, occurring over millions of years. The Himalayas, for instance, continue to rise even today as the Indian plate pushes northward into the Eurasian plate. This process is called a convergent plate boundary. At these boundaries, the intense pressure and friction can also lead to the formation of deep ocean trenches, such as the Mariana Trench, the deepest part of the world's oceans. Where plates slide past each other, known as transform plate boundaries, tremendous stress builds up, eventually releasing in the form of earthquakes. These boundaries are often the sites of significant seismic activity, as the stored energy is released suddenly, shaking the ground and sometimes causing devastating damage. The San Andreas Fault in California is a prime example of this type of boundary. Stretching over 800 miles, it marks the boundary between the Pacific Plate and the North American Plate. The frequent earthquakes in this region are a direct result of the plates grinding past each other. At divergent plate boundaries, where plates move apart, magma rises to the surface, creating new crust and often forming volcanoes. This process is most evident along mid-ocean ridges, such as the Mid-Atlantic Ridge, where new oceanic crust is continuously being formed as the plates separate. The ring of fire encircling the Pacific Ocean is a testament to the volcanic activity associated with these boundaries. This region is home to about 75% of the world's active and dormant volcanoes, and it is a hotspot for earthquakes and volcanic eruptions, highlighting the dynamic nature of our planet's surface. The story of tectonic plates is not a tale of the past, but a continuous process that shapes our planet to this day. The continents continue their slow drift, moving at about the same rate as your fingernails grow. The ocean floor is constantly being renewed, with older crusts subducting or sinking back into the mantle at convergent boundaries. This cycle of creation and destruction has been going on for billions of years. The movement of tectonic plates has profound implications for the future of our planet. Geologists predict that in millions of years, the continents will once again converge, forming a new supercontinent. This future landmass, sometimes called Pangaea Ultima or Amarsia, will have a vastly different climate and geography than our current world. The ongoing dance of the plates will continue to reshape our planet, creating new landscapes and influencing the evolution of life itself. The study of tectonic plates is a journey into the depths of our planet and the vastness of geologic time. It's a story of immense forces, slow but relentless, constantly reshaping the world around us. So, keep exploring, keep asking questions, and never stop marveling at the wonders of our dynamic Earth. For within its fiery heart and beneath its shifting surface lies a story as old as time itself. And as always, keep looking up and down. Subscribe to learn more about the mysteries of our universe.